Welcome, everyone. Thank you for being here to demo some cool things. Today we have a shorter list than usual. So if you want, we have 4 people, and mine at the end is a short demo. So if folks want to take a little bit longer, I'll allow it today. So we'll have Rick talking about Dask Expressions and the recent work that has been going towards there. Matt Powers, he's going to taught us or show us some of the work and some of the integrations with Delta that he's been working on. And then Miriam, you mentioned you are chipping in for Fabiana. So I'm going to talk a little bit, if I recall correctly, about ydata-profiling and then how it's implemented in Pandas and I believe Spark and other stuff, and then see if it's a good fit for Dask. And then we can probably get some folks interest and then see if we can get it added to Dask or involvement to Dask. And then at the end, I'll show a quick demo on the most recent work that has been going in Dask-bigquery, and then now you can not only read, but also write using Dask and BigQuery. So with that being said, let's kick it off with Rick. Rick, you want to take the lead and then go for it.
Yeah, sounds. And I'm sorry if my volume is, or my sound is weird. I always have headphones on and Zoom doesn't allow me to use them anymore. I don't know what's going on, but I'll figure it out. All right, let me make sure I'm sharing the right screen. Yeah, I guess I'll just dive right in. I don't have a nicely polished presentation or anything. I really just have a notebook that I've sort of started adding things to give some examples of the kinds of features that we've been adding to a new library called Dask Expressions. So this was originally started by Matt Rocklin as an experiment, and then I joined in and started adding features. So yeah, there's a link somewhere in here about some of this is taken from the notebook that's actually in that repository. But yeah, I'll dive right in and I'll start with the motivation of like, why are we even working on something like this? And so for those of you who aren't familiar, I'll give a little primer on high-level graphs and what they are in Dask data frame. And so the high-level graph concept was somewhat recently introduced a few years ago into Dask data frame, Dask array. And the whole point is really that instead of carrying around a low-level graph, when I say low-level graph, I mean a full dictionary of tasks for every partition or chunk in your collection, you carry on something called the high-level graph. So if I were to come here and import time series, here I'm gonna restart this. I'm starting fresh, and then we'll see that the Dask object on mean here is a high-level graph rather than a dictionary, right? And if I visualize it, I see that I have what are called layers. And so I don't see a whole bunch of individual tasks for all of my partitions. Time series carry around 30 partitions or so. So if I actually looked at the full materialized graph, I would have a lot of little boxes here, but this is just a high-level graph. And so the introduction of high-level graphs was useful. I mean, it does a lot of nice things. It makes things like column projection easier. So if you do something like select certain columns after doing a reparquet, we can actually look at these high-level graph layers and say, well, actually, we should add a column selection inside of the reparquet layer. And it also made things like high-level task fusion possible. Like we can fuse tasks before we create the low-level graph if we know that there's two blockwise layers adjacent to each other. With that said, the column projection is still pretty limited. And the following optimizations like predicate pushdown, join reordering, using statistics to rewrite the graphs, this is all pretty much remains elusive. And the reason is pretty simple. If you look at the Dask data frame or really any collection API, in order to initialize one of these collections, what you end up needing to do is pass in a graph. Now, we made this new change, a few years ago, right? High-level graph. So this could be lazily created at, excuse me, the graph can be lazily generated at compute time, but we still are very separately passing in things like the name of the collection, the metadata for the collection, divisions for the collection. And so all of this metadata has to be created before you even initialize your new collection. And it's managed in a very different place from where your graph is ultimately generated. And so what this means is it becomes pretty difficult to regenerate. It becomes very difficult to regenerate your high-level graph in like a general way, which is pretty important for some of these high-level optimizations that we would want to do. And so this has, we've tried to make lots of small changes within Dask data frame or Dask array incrementally to get to something where we can regenerate the graph. But what we ultimately decided to do is to experiment with what a final solution might look like separately so that we can move a little faster and figure out the design somewhere separately. And so this brings us to Dask Expressions. And so just a quick start of Dask Expressions. There is an alpha version available here. I wouldn't recommend you build anything off of it, but if you want to kick the tires and play with it, you're welcome to try it out. But yeah, so I'm going to import Dask Exper as DX up here. And just to note, we have a few different methods for creating collections right now. There's from pandas, there's the time series, we have read parquet and read CSV. So I'll start with the time series here, and you'll notice that I just have there's nothing fancy in the repr, but you can see that it's carrying around a time series expression, which I'll talk a little bit about later. But what you need to know right away is that this is really just a collection, just like Dask data frame collections, and so you can use compute persist head to execute the graph just like you would in those other collections. And for the rest of this, I'm going to try to use Parquet a little bit. So I'm going to convert to Parquet. You'll note here that we don't actually have a to Parquet yet in Dask Expressions. This is not particularly difficult. We just haven't gotten around to it yet. All right, so what is the basic class structure here? So for example, let's say I project column X from that time series data set and add the value of 1. So now I have a series incremented by 1. You'll see that I have a collection just like I would have in Dask data frame, but this collection actually only holds on to one thing. It holds on to an expression object, EXPR, right? And so this in the wrapper up here, you'll see that it's a read parquet expression plus 1. It looks kind of like symbolic in a way. Here we have it below here. And so these expressions have a hierarchy. So if I take the series expression, I look at the type, it's actually an add, right? Because I added a read parquet expression with a literal value of 1. And this add expression is a binop expression, which is a type of element-wise expression, which is a type of block-wise expression, which at the very bottom is an expression, an EXPR. And so expressions also, they can have their own operands. I don't know if I included operands here. So an expression, I removed the cell that has operands, but the only thing that an expression really holds on to is something called operands, and operands can have names. Like here, the add expression has a left operand, which is that right now is the read parquet expression. And you'll notice that since operands can also be expressions, what we really have is an expression DAG, which is, if there's any confusion about that, I'm happy to chat a little bit more, but that's pretty much the whole point here, right? So, and our Dask collection is now carrying around a single expression object, but that expression object really corresponds to a graph of expressions. All right, so now let's look at some visualization, because once you start working with this, you're going to kind of wonder, well, okay, I have a DAG of expressions. What do things actually look like? What do I have going on right now? So for this particular series where I want to filter on the ID column and then add 1, you can use something called pprint, right? That's always useful. And so for series, preprint, what I have here is the very top level expression that I used was an add. And so I can see that I use add and I have a literal value on the right of 1. And what I'm adding is the output of this filter expression. And the filter expression is taking an equals expression and filtering by some projection, or taking a projection and it's filtering by some equality. And you can just keep diving down further until you see what is the root. The root is the read parquet. And then we can also use visualize this to look at this in a little bit more of a visual way, right? So this is just showing the same exact information. There's the pretty print representation, the visualized representation. This is very useful when you start playing with the library and want to make sure you know what it's doing and you can understand what kind of optimizations it can do. And so how is the actual Dask graph generated when you're doing this when you're using this library? Well, every expression has to has a layer method. And unlike in Dask data frame or Dask array, we're not generating a high-level graph layer here. We're actually generating a low-level graph layer because the optimizations are not done within high-level graphs. So right now, you see the layer here is really just, I just have two partitions for this particular case, but the read parquet layer is just producing the tasks that Dask actually needs to schedule. So now the more important part of why we're all doing this, optimization. So right now, in the future, there are lots of ways that we can add optimizations, and there are other optimization passes we can do, because what we now have is an expression system that is able to rewrite itself, which is something we are completely missing before in Dask data frame or Dask array. And so the two types of optimization passes we have now is called, the first one is simplify. This just means that we traverse the expression DAG and we let each expression change itself, knowing its own, knowing what its dependencies are. We also, for each expression, go to the children and ask, do they want to change their parent? And this allows you to kind of push things down the graph or push things up the graph in a way and reorder things. We also have a fusion.
1 minute, Rick.
Sure. I'm almost done. I don't have to go into detail after this stuff. And then there's also fusion, which just means, hey, sometimes we want to combine, when we actually generate the low-level graph, we want some tasks to be fused together. And so you see the simplify for that particular example before. We start with this. After we simplify, actually everything gets pushed down, the add, the filter, we have a column projection in read parquet, and we have a filter added to read parquet. So we have predicate push down and column projection. And then we're just adding the result of that with the literal value of 1. And you can see visualize does the same thing. So we started with this larger graph, right? And now we have a much smaller graph. And fusion, don't have to go into too much detail about how it works, but you can also visualize it, within the pretty print. We just add these vertical lines just to show, hey, actually all of these expressions have been fused together. This was kind of a pain point in Dask data frame where you don't really know, something's fused, you're like, what is inside of this thing? Well, this is a little bit easier to visualize here. And I only have 1 minute. I'll just mention that we have the concept of abstract expressions. A lot of these expressions are not actually able to generate a graph themselves. They have to be simplified down into other expressions, optimized into other expressions. Like mean is the simple case where if you start with mean and you simplify it, which happens when you call compute, it actually splits into a count and a sum. Merge does something similar. So you'll see that we start with just merging two of these time series projections, but it actually breaks into a disk shuffle, for example, right? So it becomes easier to understand how things are broken apart when you are able to break it down like this. And so I think it's really useful. So with that, I'll just mention, we have next steps. I'm going to put this gist up online and link to it in the GitHub issue for Dask Demo Day. We're still trying to fill in the API. We need more testing and benchmarking, working on QDF support and using partition statistics to accelerate things like length and avoid unnecessary shuffles. But yeah, it's been fun. We're still pushing on this. So yeah, that's enough for now. Thanks.
Awesome. Thanks, Rick. I think we have just time for maybe one question. If not, we push the questions to the end. Do we have any questions? All right, sounds like you were very clear about it. Awesome. Next up, we got Powers. Gonna talk a little bit about like Dask and Delta Lake, and then its integration, and then what's he's been working on. So, Powers, take the wheel.
Let's talk about the architecture of a Delta table and why it's a good fit for Dask. So a Delta table consists of Parquet files and a transaction log. So when you're reading a plain vanilla Parquet data lake, you need to perform this expensive file listing operation. And then you need to gather the metadata statistics from the Parquet footers. And let's say there's like 40,000 Parquet files. So you need to like perform a file listing operation, get all 40,000 Parquet files, and then partially open them up, grab the metadata statistics, and then you have all that data. Well, that can be really time consuming. I think Dask actually was originally doing it with a single text file that wasn't scalable. I think Rick knows all about this stuff. So basically, just it turns out that grabbing that information directly from a transaction log is a lot faster and more reliable. And the transaction log also makes it a lot more flexible for stuff like ACID transactions and consistency and reliability, time travel, that kind of stuff. So let's take a look at a query on a CSV file and then compare it the same query on a Delta table. And then think about why the Delta table is able to make it faster. So in this case, we're using this H2O group by dataset. This is just the 5 gig dataset that I ran on my local machine. So when we run this query on the single CSV file, we can see it takes 9.2 seconds when we're using CSV. And when we run this same query using a Delta table, we can see that it only takes around 5 seconds to execute. And that's because we are skipping files. So we're looking at the transaction log, we're inspecting the min and max values, and we're saying, well, only a subset of this data needs to be read to execute this query. We can skip entire files. And that's basically how the query is going to execute a lot faster. Let's go here. So this little code snippet is powered by this deltadask library I've created, which is, it's not really a library, it's like 4 lines of code, which I will show shortly. There's another implementation of deltadask, which is this Dask Delta table. So one action item for the community is to kind of think of one of these libraries on a go-forward basis and just select with one of them. Hopefully we stick with this one. I would rather use this library and just improve upon it. It seems like it has more traction. So hopefully we can incubate one of those. Let me see how I'm doing on time. Oh, I'm doing pretty good on time, so I can talk about some code stuff. I stopped sharing. That's not what I meant to do. Let's take a look at the code. This is the deltadask project. You can see that basically all that's happening here is we're reading in like, this is 5 lines of code. We're instantiating a Delta table object. This Delta table object is based on the Rust implementation of Delta Lake. So Delta Lake is implemented in Scala for the Spark bindings. It's implemented in Java for like the Trino bindings and the JVM ecosystem bindings, but it's also implemented in Rust. The Rust implementation gives Python bindings that have no JVM dependencies. So we can use, it's kind of indecipherable from any other Python library, this Delta Lake implementation. So basically what we're doing is just some PyArrow magic and grabbing the relevant files based on the filters. And we are unit testing this with kind of our standard unit tests. This is Delta acceptance testing. So these delta acceptance tests contain a bunch of reference tables. So like we have this all primitive types. And in all primitive types, we have this delta table, and we have these expected values. So what we're doing here in this unit test is we're saying, when we read in this delta table, when we read in this Parquet file, we expect both of those to be equivalent. This makes it really easy to check that our connector is working as expected. It also makes it easy to check that our connector is properly implementing time travel for the different versions. Okay, so that is delta dask. Let me go back to my presentation. Where'd my presentation go? Slides. Okay. So I guess our next action items are to kind of select one of these libraries, get it incubated. Then we can hopefully create a Delta Dask Slack channel in the Delta users Slack organization, so we can chat with some of the Delta Rust core developers along the way. And hopefully we can get all the reads set up, and we're building some additional infrastructure that'll make it easier to write to Delta tables with Dask. To kind of complete this conversation, give everybody some homework. There are three main lakehouse storage systems, Delta Lake, Iceberg, and Hootie. I don't really think Hootie is too much of an option now. I know that Martin Durant made a Iceberg Dask reader. I was looking for it, but I couldn't find it. I think the thing with Iceberg is it's a little bit more intertwined with the JVM and Hive metastores. Delta Lake plays nicely with a Hive metastore, but also without a Hive metastore. I don't know if Iceberg plays well without a Hive metastore. If you would like some additional reading, I highly recommend reading these papers. One is on the lakehouse architecture paradigm, which I think is very relevant for Dask. And the other is in this paper that compares the lakehouse storage systems, Hootie, Iceberg, and Delta Lake. So feel free to ping me anytime if you'd like to collaborate on this connector. I think it's a huge benefit for the Dask community.
Awesome. Thank you, Powers. Do we have any questions?
I have a quick question.
Hey, Powers, just walked in. Oh,
go ahead. You can go ahead.
Go ahead, Rick.
I would just did I see correctly that the approach is effectively to convert to a Pyro data set within the Delta Lake? That's pretty cool. So you can pretty much, once you have the data set, you're kind of interacting with it in the same way that like the read Parquet can interact with it. Because all right, I just wanted to clarify that sounds useful.
Yeah, the guys who are making the people who are making Delta Rust are also Pyro people, so they love Pyro data sets. That was the implementation. I'll send it to you, Rick.
Hey, Powers, thanks for the chat or the discussion. Can you say more about writing? Like, what I assume writing is like way harder than reading. It's exciting seeing how easy the Python bindings are around the Rust library to make reading easy. I imagine writing's harder. Can you say more? Like, do you expect that to be a heavier lift?
Writing's harder. Basically, we're building out infrastructure to make writing easy. Because like, right, we're building connectors, all sorts of connectors for different people who want to write. We don't want to reinvent the wheel. So we're going to expose APIs to make building the writers easier. They don't exist yet. They're in development, but the idea would be for Dask to plug into those rather than to figure that all out yourself.
That sounds great. Do you have a very rough timeline? Is that like a week, a month, a quarter, a year away?
It's a great question. I wish I had the answer to that question. Probably more like, hopefully a quarter. but don't hold me to it.
Yeah,
But yeah,
expect a
like,
lawsuit in 3 months.
so basically, the higher level answer for that is like data lakes are easily corruptible because they don't support ACID transactions. In order to support ACID transactions, you need reliable transaction guarantees, serializable, concurrency control. In order to have that on multi-clouds, it's hard. So that's why the writers are significantly harder. I think it's a lot easier to make reliable transaction guarantees on GCP and Azure. S3 doesn't make it easy because they don't have like a put if absent operation. But anyways, ACID transactions are great because you're not corrupting your data, but it's also hard.
All right.
Cool. Thanks.
That's very cool. Great to hear from you, Powers. If anyone has more questions, then we'll leave it at the end when we have like some more room. Now we are going to go for with Miriam, who's going to talk about like why data profiling, and then what's the work been done in there, and then see if this could be a good suit for Dask. So Miriam, take the wheel.
Yeah. Okay.
Yep.
So essentially, why data profiling now with support for Spark data frames is the successor, or would you say a new version from pandas profiling. So essentially, it is one-liner package where you can get all of your data profiling done simply. Installing is really simple. You can just create a virtual environment and installing through pip or conda. And using it is really a one-liner. So you just need to import your, for instance, pandas data frame, get your profile report on, and then after you read the data, you can just generate it like this, the profile report, and you can show it in a widget so that you can use it right there on your Jupyter notebook. The main overview of the profiling report is quite comprehensive analysis of the quality of your data. So you do have an overview of the essential data statistics. So number of features, number of observations, what type of features do you actually have? And then the most interesting and data-centric part of it is the alert section. So you can have a sneak peek of what your data looks like and where do you need to probably take action. This is very helpful when you have, for instance, large pipelines where something changes along the way, when you are trying to make a new upload of your data and the schemas have changed, requirements have changed. And it is very helpful for other use cases, which I will mention just briefly. So essentially, you have a quite comprehensive amount of data quality issues. They might respect to real errors in processing of the data, or perhaps just simply naturally arising characteristics of your data that is for you to then check out with a little bit more thorough. And then you have both univariate and multivariate analysis of features. So you can zoom in to each feature, check properties such as the deviation, kurtosis, mean, histograms, common on extreme values, and you can analyze the particularities of some features where you can identify, for instance, if there was an error during the processing or loading of the data. After this univariate analysis, you have the correlations and interactions, which I will just jump in. So you can check how values can be related to each other. If there are some insights you can take right away from here, and you can see them all also in the correlations. So you can check which features are related to each other, which ones you can, for instance, discard if you are going to devise a machine learning model, and what characteristics do you need to be aware of when accounting for your downstream applications, what you need to preprocess here. Finally, we have the missing values sections, which is something very common in real-world applications. We have both the count, matrix, and heat map. Sometimes you can even diagnose some more difficult data, missing data mechanisms from here, depending on the relationship that this absence has. And you may find your first, last rows and duplicates. In this case, they are none in this data set, but you can find duplicates also in the end of the report. Then for saving options, you have the HTML, you have JSON files, so you can easily incorporate into other applications. And of course, this was a scenario for tabular data, but you can also do it for time series data. So for the particular case of time series data, what you will find is different types of alerts that can emerge, such as the non-stationarity and the seasonal patterns that can happen in your data. And you can right away identify, for instance, situations, verify the auto correlation and the partial correlation graphs, which are one of the most indicative or illustrative information that you can take out of this data. As I said, there are plenty of use cases right away from getting the profiling report. You can easily make a one-line exploratory data analysis. You can do quality assessment, management, troubleshooting, and you can do a lot of compare in terms of data transformations and the types of properties you may have when you are developing your models or deploying your models into production. So one nice functionality we have been working on is the comparison report functionality. In this case, I'm just showcasing an example for a data imputation strategy. So what I'm doing here, there was a feature with a lot of missing data in my original report. I noticed it, and then I'm just going to use a mini imputation strategy to see how things go in the transformed data. Then I generate a profile report for this transformed data, and then I use the compare function to generate the comparison report. So it looks very similar to the standard report, but what we have is a side-by-side comparison of the features, the alerts, and then both features in the original and transformed data. So if I go to check the ferritin, which was the one I imputed, I can right away see that, well, there are no missing values, but perhaps this was not the best strategy to use, because since this original histogram has some large values, they all impute right away in the mean. So this is actually distorting. So you can see right away that it was not an appropriate choice. You can do it for other use cases in this compare. You can, for instance, compare real data with synthetic data that you generated. You can use it to evaluate data augmentation strategies. You can use it to check for drifts. So if you have something that is changing over time, you can compare, for instance, the properties of your training and test sets when you are performing divisions for model validation. And you can also check what types of effects these transformations have on your interactions between data. So we can find here the effects of imputing with the mean. You have these depth patterns in the interactions between features. So all in all, ydata profiling is something that offers a really widespread amount of use cases. It has been crazy for Pandas users, now for Spark users as well. And we're hoping to get the Dask community working with us as well. So this would be amazing, I would say, to have in Spark. It would open a lot of use cases also for your community. And so this is a call for help for us to collaborate more and create ydata profiling on Dask. And that's it on my side. Thank you.
Awesome. Thank you very much, Miriam. Do we have any questions?
Miriam, question for you. So can you say a bit more about the it's cool technology. Can you say a bit more about the some users that have used ydata and had a good time with it? There's lots of features you just mentioned, what's the most common feature you see used? Where has that been helpful?
Yeah, the most common is definitely the standard profile report, because when you don't have any idea of what your data looks like, and even when you are an initial user, you often don't get very exposed to some of the issues. Sometimes people don't really understand what is imbalanced data, for instance, or what is missing data and how to handle it. So for some users, this is the first contact with some data characteristics, and this is perhaps the most widely used in newbies. For more experienced users is the comparison report. So we want to be able to any point check how our transformations and our operations over data are impacting our decisions, and how can we adjust that for the final pipeline. And so these are most often the use cases users are trying to get more feature requests on, and so on.
Cool, thanks.
Thank you.
Any other questions? So I have a question. If there were folks interested in collaborating or start working on this, how would that go? How would that conversation get about? Do people just post an issue on the repo? How do we get this going? Yeah.
Okay, so we actually have started a branch for this. I can put it right up here. And yeah, we have a very supportive community. We can perhaps start a discussion there, see who's up to working on this. We normally do a lot of sessions, either from entry level to more experienced level type of projects. So we like to support the community a lot, and we follow up with this project. So this is how we probably start, not just with short sessions. Let's discuss, let's find a roadmap, let's get started on creating this. And then, yeah, following for GitHub issues or discussions, but our community actually works very well on that account. Yeah.
Awesome. Thank you very much.
Thank you.
Do we have any other question? If not, then I'll take the wheel now. I'm going to be showing you a little bit more about the progress on Dask-bigquery. This is mainly the work from Irina Trong that most recently has been working on BigQuery, but she's in the West Coast and it's very early for her. I think she's taking kids to school. So I'm going to try to do my best to show this. So let me share my screen. Dask-bigquery is a project that started like around 2021, where we initially got an implementation for reading from BigQuery. And then it kind of like it slept for the time until most recently that got picked up again. And then there was some work on writing to BigQuery. So today you can read with Dask, you can read BigQuery tables, and then now you can also write. So I'm going to quickly show a demo just from a local cluster, so a super simple read and write. And before that, like if you are interested in contributing or collaborating, like there's a Dask-bigquery repo, and then you can go and check it out there. There's some action going on, and then some talks about credentials and BigQuery credentials and Google credentials, which are a little messy. But yeah, if you have expertise in this and you want to like share it with the world, then go ahead and then chip in. So here I'm just going to just import Dask-bigquery. So Dask-bigquery, you can pip install it or const install it. And then to get set up, currently you need like a service account. We're working on trying to make it work with like the default login account that I was having some issues with that. So I'm going to show you today with the service account, but you can go and then get some in the Google documentation. You can see how to set up a service account and then get the JSON file to be able to activate those credentials. And then there are like a couple of permissions that you need to tweak and then add one by one. Thanks to Nat that patiently tested which were the minimal ones. Here in the README, we have like what's the minimum roles that you need for read, and then what are the minimal ones that you need for writing. So one small caveat for writing to BigQuery is that you need to have access to an intermediate Google storage bucket. So you cannot write directly to BigQuery. So you'll need to write to a storage. So you will have to have access to that bucket and permissions to be able to write to it. And then from there, it will write to BigQuery. So here we have just probably like a cluster. And we have like our all-time famous time series. So I'm just going to create that data frame. And now I'm going to write it to BigQuery. By default, it will create a bucket, like if it has like you need to have those permissions. You can provide a bucket that already exists by passing the bucket keyword here, but do have that. So you'll see that this is doing a 2 Parquet and a storage one over there. And for some reason, I'm having an error. Okay, this already existed, so I didn't know that. So let's just switch this. That's some weird stuff. We'll need to check on that because if it existed, it should have done something. And now if I want to read it back, so I need to modify this one over here. So we can just read this. Then I can do a head. And now we do have like the one that we just read and write. So in BigQuery, you will have, this is like the place that you already need to have a project set. But here is our data set over here. So that's the table. And then it has these properties. And then you can see a preview. And you have all this stuff here. And the bucket, it will write to this bucket and it automatically cleans what it's there. So then you don't have to worry about that. And last one thing from the reading, BigQuery has this cool thing that you can kind of row filter. So that and Dask BigQuery also have that. You can provide a row filter, for example, by name. And in this case, let's just grab all the ones that are named Bob. This one was this. So if we do that, then we can just go ahead and then just do a compute. This is a small data set for the sake of the show, but then we have only Bob's on the name. So that's BigQuery, kind of like in a nutshell. There's still work going on there. If you try it and give it a try, leave probably a comment, or you probably run into some issues or something. We're happy to take your input, and then, yep, that's it for me. If we have any questions, I'll happily take them.
Quick question on Google BigQuery stuff. I might have missed it, but did you, so you're writing to Parquet as an intermediate place, and then presumably that's getting cleaned up afterwards. Yes. Did you have to specify a bucket to use? Like I might have missed that before.
Yeah, by default, we create a bucket that it has a name, and you will need to have like permissions like to create a bucket to do that. But you can provide a bucket that already exists, and you just pass the keyword bucket. So let me see if I have any examples here. Nope, but like if we look at the code.
Okay. You guys are showing your screen, but that's okay too.
Yes, no, I was. But yeah, that's kind of like, yeah, the answer. Yep.
And I've seen people who do this like manually, not with the project, but they'll specify like a retention, like a relatively short retention window on the bucket. Is the automatic thing doing that as well? In case like your program breaks halfway through, you've not got this like weird bucket hanging out that you like don't know exists.
Yeah, actually, we recently noticed that I think there was something breaking in CI. We couldn't get like the MAC instances and stuff, and then some parts were like halfway there. It's not doing the cleaning properly, so we're working on fixing that. But yeah, that's a good question. Yeah, because if it breaks halfway there, it won't go all the way, and then you'll get things hanging in there, and that'll probably imply charges for what you are storing. So yeah.
Only there was some like really nice, ACID compliant distributed storage system that people could use to write from Dask.
Yep. Free the data.
All right. Thank you all for being here today. That being said, I forgot to open a separate issue because I was like on vacation for this. But I will open one and then I will ping you separately to drop the links of all the content that you shared today. And then when the video recording is up on YouTube, then it will be added to the playlist, and then I'll ping you all again for that. Thank you very much for your demos today, and then I hope you have a great rest of your week. See you all.
Thank you.
Thanks, everyone. See you.